Hey everybody, we're back to trigonometry again. This is a section on graphing sines and cosines, our initial attempt at it. This is section 6.3 in our book. In someone else's book, it's probably 2.3 if you're at another school. This is trigonometry again, and we're looking at graphing sines and cosines. So section 6.3, graphing sine and cosine graphs. Before we get started, I want to give you some terminology. A periodic function repeats itself with a predictable pattern. If the pattern is P, or it's called the period. If the period is P, after you go right on X, P units, the graph starts to repeat. Same thing going left. What this means in terms of a function, f of x is equal to the same thing as f of x plus p and any multiple of p. So n is an integer. For sine and cosine, base graphs, p equals 2 pi. And it's related to the unit circle. We go around the unit circle and it goes, we know this is 1, 0. And as you go, x ends up being the angle when we graph it. And the y value, notice it goes, we go around and around and around and around. It starts to repeat once we've gone 360 degrees, or 2 pi in radians, because 2 pi is radians are just a number, and that's how we graph. We graph numbers. It starts to repeat. So it's related to that. So sine of x is the same thing as sine of x plus n times 2 pi. And same thing with cosine. We tend to write this as sine of x plus 2 pi n. And similarly, cosine equals cosine of x plus 2 pi n. So let's take a look at graphing this. I'll pause and let you pause this so you can do this. Graphing these by hand is really easy. Once you've done it a few times, not a lot changes. So, graphing a function, remember we have f of x. When we're graphing it, f of x equals y. And we're going to say y equals sine x. So x is basically theta. So what do we have? Let's just plug in the ones on the quadrants. We've got 0, pi over 2, pi, 3 pi over 2, 2 pi. When I stick in 0, sine of 0 is 0. Pi over 2 is 1. And this was repetitive, except the 3 pi over 2 was negative 1. And notice this is where it starts to repeat. Those are equal. So when we graph it, mark your y and your x-axis. Give it a height of 1 and -1. And just go out a certain ways, mark it, cut it in half, and cut each of those in half. So you have 4 dashes. This is the pi over 2. This is pi. This is 3 pi over 2. And this is 2 pi. The sine graph follows. This is our y value. So when x is 0, y is 0. When x is pi over 2, y is 1. When x is pi, it's 0. When it's 3 pi over 2, it's -1. And when it's 2 pi, it's 0. And this makes a nice rolling wave. And it keeps repeating. In fact, it goes like that way, and it keeps going like that way. Let me load this up on Desmos and show you what I'm talking about. Sign in. I got some of these already saved. Where is my trig? Ah, well, let's just type it in. Let me switch over and share with you my Desmos screen so you can see how I'm doing it. So I'm going to say y equals sine of x. Okay. Notice it makes this nice little rolling wave. In fact, when you do it, notice it tells me pi over 2. It doesn't try to give me a decimal approximation. It gives me pi, 3 pi over 2, 2 pi, and it starts to repeat. 5 pi over 2, 3 pi, 7 pi over 2, 4 pi. In fact, sine is 0 at every multiple of pi. 5 pi. And you'll see it goes the other direction as well. Okay. So let's go back to our graph. As we saw in Desmos, y equals sine x equals 0 when for x equals n pi. Any multiple of pi equals 0. And the halfway points bounce between 1 and -1. And while what I have here looks somewhat like a circle because I didn't make this stretch out far enough, my 1 and my pi is over 3. It should be much longer the way I did it, and I didn't do it very well. But I was trying to fit it on one page, and that's fine. It's like I shortened my x-axis is what I did. This is called a sine wave. Another name for it is called sinusoid. It just means a sine wave. And again, the period is 2 pi. After 2 pi, the graph starts to repeat. if you look at it, if you so sine, if we go backwards, sine of negative pi over 2 is -1. And the reason why I'm saying this is if we stick in sine, if we stick in negative x rather than x into sine, what pops out is negative sine x. If I stick in pi over 2, I get 1. If I stick in negative pi over 2, the 1 becomes negative. When these functions that like this, when f of x or f of negative x equals negative f of x, these are called odd functions. Okay. I'll pause again, let you finish writing this down. Hit pause if you need to. So the fun things about odd functions are symmetrical about the origin. What this means is, let me try to draw it reasonably. So if that's 1, 1, 2, 3, that's about pi. Pi over 2 would be right about there. And I got to go backwards. Okay. So symmetrical about the origin means if you start at the origin and go to the graph, draw a straight line to the graph in any direction, you can draw a straight line in the exact opposite direction and hit the graph again at the same distance. So if this is a distance d, that's a distance d in the other direction. The way I remember symmetry about the origin, this is how I graph them. This is the way I remember to graph them. About the origin. What I do is I flip the graph over the x-axis and then the y-axis. You can do it in the other order, flip it over the y and then the x. So if I flipped it over the x, it would come down like this, it would be like this. And then I flip it over and it hits here. That's how symmetry about the origin works. If we take a look at f of x equals cosine x, make our same table. 0, pi over 2, pi, 3 pi over 2, 2 pi. When we stick in 0 into cosine, we get 1. And now all the ones that are divided by 2 are zeros. Cosine of pi was -1, and cosine of 2 pi was 1. And that's when it starts to repeat. Again, break it up into, make it 4 pieces long. 2 pi's over here. We got pi right here, pi over 2, and 3 pi over 2. And we plug in what we have up here. When x equals 0, y equals 1. When x equals pi, y equals -1. and 2 pi's back up to 1. And then those quarter points, the pi over 2 and 3 pi over 2 are 0. And again, it makes a nice rolling wave. And it keeps going. Load this into Desmos. We'll flicker over to look at it. We can see when y equals cosine x, we start off at 0, 1. At pi over 2, it's 0. At pi, it's -1. 3 pi over 2, it's 0. And 2 pi, it's 1. These values are from the unit circle. So that's why I said memorize the unit circle. You need to know it. It's going to pop up. Okay? Again, the period is 2 pi. And cosine is called being symmetrical. It's an even function. So when f of -x equals f of x, you have an even function. This is just symmetrical about the y-axis. I don't think I'm sharing the right screen yet. Yeah, where did I stop sharing? Let's go back. So as I was saying, we drew the graph, we showed Desmos. These values I got right here are from the unit circle. You need to have it memorized. The period is 2 pi again, same as sine. When f of -x equals f of x, it's an even function. That's what we call them. It's symmetrical about the y-axis, and this is the case with cosine. It's cosine x, and that's the same thing as f of -x. If I stick in pi over 2, well, let's try pi. If I stick in pi or negative pi, just look at it. Our unit circle, if I go pi that way or pi that way, I'm still at the same point. If I go pi over 3 or negative pi over 3, my x value is the same. Or the what? It's the same thing as having the x in there. I'm sorry, symmetrical about y-axis. Same y value. Okay. For both, I think I said that. Ignore that graph. F of x equals cosine x and equals f of -x. If you stick in -x, it's the same thing as f of x. Something's off there. Let me come back to that later on. I'm screwing something up there. No, that's right. When y equals cosine of -x, It's the same thing as cosine of x. Okay, so for both sine and cosine, the graphs y equals sine x, y equals cosine x. Oftentimes they don't even put the parentheses. You should have them there. It's technically there. For both the domain, all acceptable x values, it's infinite. Negative infinity to positive infinity. The range, though, we saw it in Desmos for both of them. The lowest it could be was -1. The greatest could be was +1. Okay? Those are the base graphs. Where we're going to eventually get to is y equals a times f of x. We'll do that. We'll do y equals fb of x. And we're going to even do a lot more than that. This is what we're going to cover today, though. So let's take a look at when we have a number out front. A and b are numbers. How do they change the graph? Let's see how they affect the graph. Y equals a sine x or y equals a cosine x. If you do your charts, I'm just going to do sine x. You'll see how it works. We got 0, pi over 2, pi, 3 pi over 2, 2 pi. This was 0, 1, 0, -1, 0. And then when we multiply it by a, 0 times a is 0. 1 times a is a. 0 times a again is 0. Negative a, and we're down to 0 again. The only thing that changes for y equals a sine x is now, rather than this being 1 and -1, this is a or negative a. We still have zeros at the multiples of pi. And the pi over 2 and 3 pi over 2 are either 1 or -1. So it just affects the y value. The a is a multiplier on the y values. A stands for amplitude. And it's effectively 1/2 the max value minus the min value. What I mean by that, if we look at y equals 4 sine x or cosine x, same for both. The maximum value is 4. The minimum value is -4. And a equals 1/2 times 4 minus -4 is 1/2 times 8, which equals 4. That's how up and down it goes. The reason why I tell it to you like this is if you look at the graph, or if it's not centered on the x-axis, We're going to do translations in 6.4 where it moves the graph up and down. When the graph moves up and down, that amplitude is still, you take the top value and the lowest value, you find the distance between them, and you cut it in half. Okay. Let's look at this in Desmos and see what happens. So I'm going to say y equals a times cosine x. And I'm going to add a slider for it. Zoom out a little bit. And as a gets larger, the graph gets taller. It stretches it out vertically, makes it really tall. The zeros are still in the same spot. Pi over 2, 3 pi over 2, 5 pi over 2. The zeros are in the same spot, but the amplitude that peak it's at is at A. And when A is less than 1, it gets shorter. That would be 0, 1 right there, but now it's really short. When it goes negative, when A goes negative, look what happens. It flips the graph upside down. So I recommend playing around with this stuff in Desmos. Let's go back and write out some of this stuff we said. So the amplitude A vertically stretches the graph. And I'm going to say for the A greater than 1, it's also when A is less than -1. So I'm just going to say the absolute value of A. And it shrinks the graph. It compresses, shrinks or compresses for -1 is less than A less than 1. Another way of writing that is the absolute value of A is less than 1. So that's that. What happens if we put the coefficient on the inside? What about y equals sine b of x or y equals cosine b of x? Again, b is just a number. It's a coefficient on x in this case. So, well, this is how we can look at it. When y equaled sine x, our period was 2 pi. Let's take a look at what happened on the period of 2 pi. For 0 less than or equal to x less than or equal to 2 pi, there was a fixed thing and it repeated. What happens when we make it b of x? And if we divide everything by b, we get 0 is less than or equal to x, which is less than or equal to 2 pi over b. This is the period now. The period equals 2 pi over b. Okay? The book teaches doing it like this, and you might have learned doing it like this. I think graphing is easier if I multiply the top and bottom by 2, I'm just multiplying by 1, and I get 4 pi over 2b. And I'll show you why. It's a lot easier, I think. Ready to see? So let's take a look at y equals a sine x. We'll do the 4x again. We'll do b equals 4. So let's take a look at y equals sine of 4x. When we plug it in, we've got x. We don't want to use the values we were using before. I want to make my first value 0, but I want the last value to be 2 pi over b, where the period is. Or I'm going to say 4 pi over 2b. And the reason why I say the 4 pi over 2b is this is like 0 pi over 2b. We've got 1 pi over 2b, 2 pi over 2b, 3 pi over 2b. Let me make some lines in there so it's easy to see. This is 0. I'm going to make two columns. What happens on the left is what the book does. These two values here and these are equal. Do you see how the left one might be harder to remember? Left column is harder to remember. Okay. The right column is n times pi over 2b. N equals 0, 1, 2, 3, and 4. It just repeats. So when I stick in b equals 4, my x values become 0. If I stick in 4, 2 times 4 is 8. The denominator is 8. So I get pi over 8. I get 2 pi over 8. I get 3 pi over 8. I get 4 pi over 8. This is 0, pi over 8, pi over 4, 3 pi over 8, and pi over 2. This is a lot harder for me to graph looking at it this way. When I look at it this way, I can see they are all evenly spaced out. So what I'm going to do, got my 1, I got my -1. I cut it into 4 pieces. And I'm okay with you marking this as pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. Okay? Sine starts at 0, ends at 0, the midpoint 0. The top one's up, the bottom one's down, and we make a nice little rolling graph. Okay? Doing it where the denominator stays the same and the numerator is just even or integer multiples of pi makes it so I can evenly space these out, and it's easy to plot what they are. Going, where do I put 3 pi over 8 in reference to pi over 4? This is confusing to me. On how to plot. This is not. So however you like doing it, we still end up with the same values. Notice sine of 4 times pi over 8 is equal to sine of pi over 2, which equals 1. Sine of 4 times pi over 4 equals sine of pi, which equals 0. That's why we get back to the graph we were at before. Sine of 3 pi over 8, sine of 4 times 3 pi over 8. 8 is 4 times 2, the 4's cancel. This is sine of 3 pi over 2, which is -1. That's why it breaks it up like that. So this is the more of an ideal, this is an ideal way of graphing it. Find the x values that yield y equals 0, 1, or -1 when graphing cosine or sine. Graphing the trig functions. Or better yet, y equals 0, a, or -a, if we have something in front of it. Okay? Let's take a look at some other ones. God, I hope I'm sharing the right thing. I didn't even look. Yeah, I'm sharing the right thing. Okay, good. Let's work this out a little bit slower. Let's do x equals cosine, or we've got y equals cosine of 1/2 x. How does that work here? So 1/2 equals b. Okay. So b equals like 0.5. And so if I go from 0 to 4 pi over 2b, I have 0 from 4 pi over 2 times 1/2. We're going from 0 to 4 pi. Breaking this up into increments, we've got 0, pi, 2 pi, 3 pi, 4 pi. Okay? This is our period. And that's why I said use 4 pi over 2b, because this is 1 pi over 2b. b equals 1/2. 2 times 1/2 is 1. 2 pi over 2b. 3 pi over 2b. 4 pi over 2b. If you graph it another way, please do so. When we plug it in now, this is cosine of 0 still. This is cosine 1/2 times pi is cosine of pi over 2. We plug in 2 pi. 2 pi times 1/2 is pi. We plug in 1/2, we get 3 pi over 2. And we plug in 4 pi, we get cosine of 2 pi. And again, this is 1, 0, -1, 0, +1. All this does is change where you put how you label your X marks. I'll go 1 and -1. And now I repeat on 4 pi. Here's 2 pi. Cosine starts up high. Halfway point is down low. And it's up high again. And the quarter points in the middle are zeros. And it keeps going. So I can write out how I would do that. Graphing y equals a sine b of x. Let's write this out as a full process. So first off, find the period. It equals 2 pi over b, and I treated that as 4 pi over 2b. B, you want to mark the endpoints on the graph of the first period. It went from 0 to p. X equals 0 and x equals 4 pi over 2b. Then mark the midpoint and quarter points. Part D, for the y-axis, put a mark y equals a and y equals negative a. So I'll do this down here. I put in x equals 0, x equals 4 pi over 2b. My midpoint is half that, 2 pi over 2b. My quarter points are the midpoints of the midpoints. So this is pi over 2b, 3 pi over 2b. So endpoint, endpoint, midpoint, quarter point, quarter point. I'll put down a and I'll put down negative a. And finally, for x equals the even pi over 2b, y equals 0. Then first QP, first quarter point is a, second quarter point is negative a, negative a, connect the dots. Okay. Take a look at cosine x. Graphing y equals a cosine x, a cosine of bx. It's this identical to doing sine. For steps A through D. A to D. Step E, for x equals odd pi over 2b, y equals 0. Your endpoints equal 1. And your midpoint, or a, and your midpoints equal negative a. So we put our graph down, we got y, we've got x. We find our period, whatever b is, we do it. We mark down our endpoints at 0 and 4 pi over 2b. Our midpoint is at 2 pi over 2b. And we've got pi over 2b and 3 pi over 2b. We go up a height of a and down to a height of negative a. That's the same. The black writing is same for cosine and sine. A sine bx and equals y, or a cosine bx equals y. The red writing is different. Red writing is cosine b of x. So our endpoints, we have it at a and a. Our midpoint is negative a. And our quarter points are 0. I didn't write that down. Quarter points, y equals 0. And just for fun, let's do sine x on the same graph. Green writing is a sine bx. For that one, the even multiples on top were zeros. And it goes up to a and down to negative a. And you'll see they look a lot alike. In fact, let's look at these on Desmos. Let's see them both. You share Desmos. They're the same wave, right? They're just shifted. So let me go back to our writing. Sine x and cosine x graphs are just shifted by pi over 2. Okay? It's kind of neat. So let's put this all together and do a problem where we got A and B in there. Let's do a couple of these. Let's start off with y equals negative 3 sine of 2x. So what does A equal here and B equal here? A is the number in front, negative 3. B is the coefficient on x. Oops, 2. So the period is 2 pi over b, or 4 pi over 2b. I like the second one, but I'm showing you the first one. 2 pi over 2, or 4 pi over 2 times 2. They both equal pi. The period is pi. It repeats every pi. So 2b equals 4. That's my denominator. So I'm going to go out 4 pi over 4. This is 2 pi over 4. 3 pi over 4. 1 pi over 4. I'm going to mark my A. and negative a, 3 and negative 3. And for sine, the sine had the endpoints equal to 0, the midpoint equal to 0. The first quarter point equaled a, which is negative 3. And the last quarter point was negative a, so negative negative 3 is positive 3. Okay. So why don't you guys try this one? Try y equals 1/2 cosine of 2 pi x. Pause it and give it a try. So we get a equals 1/2, b equals 2 pi. So the period p, 2 pi over b, or 4 pi over 2b, 2 pi over 2 pi, or 4 pi over 2 times 2 pi. They both equal 1. Well, that's even easier. I don't even need to do this pi, this weird pi thing. I'll just write down the furthest thing out on x is 1. That makes that 1/2. This is 1/4 and 3/4. My a is 1/2 and negative 1/2. Cosine starts off at a and ends at a. A is 1/2, so we on top. If a was negative, we'd be down below. The midpoint is negative a. The quarter points are 0. And we just sketch it away. And again, it keeps going. So that's how they're going to have you doing stuff in the homework, how you graph this stuff. They'll also give you a problem where we determine an equation from a graph. So let me give you a graph and we'll work on determining it. So let's give you this. I'm going to go out. This is going to be 6 pi. This will be 4 and negative 4. And I'm going to go like this. Okay, so what do we have here? What should we do? First off, does this look like cosine or sine? Sine x had values when x equals 0, y equals 0. cosine x had when x equaled 0, y equaled a. So this looks more like cosine x to me. I see at -4 at 0 and 6 pi, it's -4. This tells me that p is 6 pi. I can get b out of this. 6 pi, either you can say 6 pi equals 2 pi over b, or 6 pi equals 4 pi over 2b. I'm going to use this one because that's what I did. I taught you to, or taught using this. Multiply both sides by b and divide by 6 pi. What happens? The b's cancel on the right. The pi's cancel on the right. 6 pi cancels there. We got b. 4 divided by 2 is 2. I've got 2 on top, 6 on bottom, or if you just multiplied, it was 4 over 12. In both cases, this simplifies down to 1/3. So I've got b, and a is the value when x equals 0. Equals y when x equals 0 for cosine x. And in this case, a equals -4. So this looks like y equals -4 cosine of 1/3 x. Another way to find that a, also finding a, I'm going to do this. It's not necessary on this graph, but if we shift this graph up and down like we're going to do in 6.4, you should be able to do it. The max value is 4. The min value is -4. So a is 1/2 max minus min. 4 minus -4 is 1/2 times, oops. Is 1/2 times 8, which equals 4, but it starts off negative. So a is, the amplitude is 4, but it's upside down. Okay. So we've got our equation. That's the kind of stuff they'll ask you. That's how we do it. 6.4, we're going to start doing what's called translations. We're going to shift the graph up and down. We're going to move the graph left and right. And it changes the equation just a little bit. Not a whole lot. Something called the frequency or phase shift comes into play. Other than that, 6.3 is done. The basic steps are the same. You mark your endpoints, you mark your midpoint, your quarter points. It's based on the period, which is 2 pi over b or 4 pi over 2b. God, I hope I'm showing the right thing again. Yeah. And whether or not your endpoints are 0 or your endpoints are a, depends on whether you're not at sine or cosine. You go from there. Peace. I'll catch you guys later.